Hello, my name is Chris Taylor from Tactical Computing Labs. Today I'm doing a presentation called ChapelX and HPX Foundation for Chapel. This work was done in collaboration with LSU CCT. Our collaborators were Shreyas, Patrick, and Hartmut. We're going to do a quick background of HPX. We'll get into a 1D heat equation study that motivated this effort. We'll talk about the ChapelX compiler, challenges we faced during the implementation. We're going to cover a suite of benchmarks we use to measure performance, and then we'll now analyze our results. HPX is an asynchronous many-task runtime system. All of its features are housed in the ISO C++ standard for data parallelism and concurrency. Users develop ISO C++ compliant code using an API that mirrors the ISO C++ STL, and all the functionality is provided for free. So you get performance monitoring, access to an active global address space, local control objects which manage concurrency and parallelism, a communication layer we call parcel port, and then the thread scheduler which does work stealing, and that sits in between your application and the operating system. HPX places emphasis on futures and futurization, meaning your C++ code ends up looking like a directed acyclic graph chained together with futures. Objects and subsequently partitioned data types like a partition vector or partition map can be instantiated across different localities. This is what our active global address space does. It tracks those instantiations across a cluster. We can asynchronously deploy remote functions and methods, which yields a form of one or two-sided communication, which at a distance looks like active messages. HPX supports classical single program many data or SPMD style application development and non-SPMD application style development. The communication layer, called the parcel port, is implemented using OpenMPI, LCI, libfabric, BSD sockets, and there's nascent support for OpenSHMEM and GasNet. HPX also implements support for OpenMP. The 1D heat equation study which motivated this effort was the following. It was published in the EuroParl 2023 workshops. Preprints available at the link below on archive. The study implemented a 1D heat equation code where the alpha term represents material diffusivity. Second order differencing and Euler's method are applied to perform the computation, and it was implemented across 10 different programs or 10 different programming languages. And along with the performance metrics, we measured software complexity using lines of code and what's called the COCOMO model. COCOMO is a suite of different metrics or heuristics for measuring code complexity. Estimated schedule effort was picked because it represents the time to implement something in a month. As you can see on the left, we've got lines of code. Chapel yields a very, very small and concise implementation of the heat equation code relative to HPX. And on the right-hand side, you can see a four-way plot where the top quadrant or the top of the chart is fast, so performance. The bottom is slow, the left is easy, and the right is difficult according to ECE. What you'll notice is that Chapel and HPX and Charm++ fall in the upper left-hand quadrant, which is where you would want things to go, right? We want easily implemented codes that have high performance. ChapelX is part of a follow-on study to see if we can close the complexity gap between HPX and C++ with Chapel. We achieve this by using source-to-source compilation, so we're going to turn Chapel code into C++ code that uses HPX. And we're going to perform a study using the heat equation code that we already have, and then a stream and gups implementation, which is provided in the Chapel software suite. We want to see what we could do in maybe 6 months of part-time effort, so we're talking 3 to 4 hours a night. We want to constrain our solution space a little bit, so we focus on single locality solution. We use the HP Cray Chapel compiler's existing lexing and parsing implementation. So we use the exact same lexing and parsing capabilities that are in the Chapel 2.0 compiler for this work. We implement Chapel's language features as an ISO C++20 library with HPX. And we support enough of the Chapel language in the compiler and in the library to generate C++ for each of the identified benchmarks. The Chapel compiler has 3 passes: symbol, table, and scope creation. We convert the Chapel AST to what we call a ChapelX program tree, and from the program tree we generate C++ code with CMake support, so users don't have to write their own make files. We don't perform any type checking, so we allow the C++ compiler to manage that with pragmas. So we stamp out pragmas that link C++ code back to its original Chapel code. Users can select whatever C++ compiler they want, but for this study we use Clang, so it's consistent with the LLVM support provided by Chapel 2.0. ChapelX should be considered a toy compiler, so we don't implement everything. We just implement what's necessary to perform the study. Challenges. Um, Chapel's compiler parse tree is called a micro AST. We naively used it, and towards the end of our study, we found out that the micro AST injects scope and AST nodes into the program structure. So as an example, if you look at the if, the else if, and the else clause on the left in the picture to the right of the slide, on the other side, you'll see what the AST looks like. And what happens is that the else if and the else get pulled into an arbitrary scope that's nested under the original if condition. What you'll also notice is that the else expression has no information about what it is at all within the context of the curly braces. The curly braces just represent an arbitrary scope. So it's really hard to determine where you are inside a conditional expression relative to everything else going on in the AST on account of the fact that the else clause isn't labeled, and that additional scope that gets injected and the way those nodes are nested under the initial if clause makes it really hard to ascertain if a variable is in or out of the appropriate scope. This complicates syntax analysis, as you can expect or would expect, and it's something we really need to address in the future. How do we support print statements and timers? Since we don't support Chapel modules with our compiler, we create a new intrinsic function for Chapel to inline C++. We call it inline C++. It provides pass-through so users can embed C++ code into a Chapel application directly. It uses the ISO C++20 support for std format. As you can see on the right, that's the prototype for the Chapel function, proc inline CXX. It accepts a string and a variable list of arguments. You can see how it's being used underneath, and then at the very bottom you can see the code that's generated by the ChapelX compiler. Benchmarks. We did our benchmarking on an Intel Xeon processor, 2.5 gigahertz, 48 cores, 120 gigabytes of DDR4 memory. We use Ubuntu Foco Vanilla, so we aren't modifying the kernel at all. We use Clang LLVM15 because it's a hard dependency on the Chapel parser and lexer. HPX 1.9.1. We also use Chapel 2.0 with Q threads. We control the number of threads used by Chapel with the environment variable listed at the bottom right. And then for HPX, we control the number of threads using a command line argument, HPX threads. ChapelX generates C++ and the project CMake files, which is great. We turn on C++20 support so we can get access to coroutines because that's what our library uses. Coroutines give us co-await and yield access and functionality, which is equivalent to a Python generator function or a Python generator expression. Here's our heat equation code. It's performed over 1 million double precision numbers. Lower is better, and as you can see, ChapelX performs very well in our strong scaling plot here. So time on the vertical, number of threads on the x-axis. Here's our stream copy performance numbers. On the left, we've got number of threads relative to seconds, so that's strong scaling. Lower is better. You can see ChapelX performs very well in that situation. The middle plot demonstrates the amount of megabytes we were able to process over time. Lower in this particular situation is better, so we've got the blue line is ChapelX, and you can see it's performing incredibly well in this situation. And then the plot to the right, higher is better, as this is strong scaling of the number of bytes relative to time over the number of threads. So it's, to some degree, it's sort of the inverse of the plot to the left. And as you can see, ChapelX is performing very well in that situation. I want to emphasize here we were performing all of our stream benchmarks over 1 million doubles. We did that intentionally to match the input size of the heat equation code. So we want to see some consistency here to see if there's any performance differentials. We can maybe learn about what's going on with HPX and Q threads in their relative compiler and application software codes. There's our stream add numbers. They're fairly consistent with the copy. Here's stream scale, consistent with the add in the copy. And then here's triad, which is consistent with the previous stream benchmarks and even the heat equation code. One thing I also want to point out, our megabytes to time plot in the middle is scaled out over 32 threads. So we actually apply a fixed 32 thread hardware accessibility to the application software when it runs in both Chapel and ChapelX. Here's our GUPS benchmark. Our GUPS benchmark is performed over 1 gigabyte worth of data On the left, we've got lower is better, our strong scaling, seconds on the vertical, number of threads on the x-axis. You'll note that both Chapel and ChapelX experience a performance loss in between 8 and 12 and 16 threads. Our middle plot, again, is time versus amount of data processed. We're scaled at gigabytes in this particular situation, so we're not doing megabytes anymore. Lower is better. ChapelX is doing incredibly well, and we're scaling out over 32 threads. And on the right, higher is better, so it's to some degree it's the inverse of the middle plot, but we're in this particular situation we're plotting the actual GUPS value. So number of threads times bytes divided by seconds divided by 1 times 10 to the 9th for gigabytes. Here's our COCOMO metrics. ChapelX boilerplate represents all the header files, all the code that gets generated by the ChapelX compiler. Chapel C++, ChapelX C++, the red bar represents just the kernel code generated by the compiler. And then, of course, the blue bar, Chapel, represents the original Chapel code that we used in our benchmarking. And the red bar is within 4 lines of code, and the ChapelX boilerplate line of code metric on the left is almost double, and of course lower is better because we're trying to match Chapel's code size. On estimated scheduled effort, it's a very similar plot where ChapelX C++ is closing the gap with Chapel itself. Our analysis, the performance delta was interesting. Our timing is done around the kernel itself, and we really think it just comes down to runtime systems. So with Chapel, we've got Q threads activated, and with ChapelX, we're using HPX. As for our COCOMO differential, we didn't achieve a 1-to-1 mapping, but we got closer within 1 to 4 lines of code without boilerplate added into the equation. This really isn't too bad considering the time investment we made in the implementation. So given the code complexity gap closed and performance offered by ChapelX, we believe this demonstrates a viable avenue of continued research. We need to really resolve that micro AST issue and get our scoping story straight. And we also need to maybe start taking a look at developing support for multi-node distributed computing. Here's a compliance statement for the clip art that was used in the first slide. And I want to thank everyone for your time and attention. Take care.